Okay, so those were the transmissions. Now let's look at where they are used and, by the way, how we can use them together. Because the way we send those signals is also going to depend on the band, but also on the subprotocol that you're using. So some flavors of 802.11 allow BPSK and QPSK in the 2.4 GHz band. And that means that with those flavors, you can go all the way up to 2 megabits per second. This is not your throughput, right? This is the speed at which you send your bits. And we'll see later on that a lot of things have to happen around that, which will make that your throughput is going to be lower than that. That's the speed of the line, as you say. So some flavors allow you all the way up to 2 megabits per second. Now, very few people use that variation today. That's the old 802.11 standard that was released in 1997. Since then, newer flavors came in that allowed you to use CCK in the 2.4 GHz band. And that allows you, as you know, up to 11 megabits per second. This variation is called 802.11b. It came out in 1999, so it's also very old. Notice that these two are only available in the 2.4 GHz band. Now came OFDM, and OFDM, the first iteration, allowed transmissions in the 5 GHz band up to 54 megabits per second with 64 QAM. That was also released in 1999 by the time 802.11b was designed for the 2.4 GHz band. That flavor of OFDM in 5 GHz is called 802.11a. And then the same flavor of OFDM was brought from 5 GHz into the 2.4 GHz band, allowing still the same 54 megabits per second, same technique, just bring it from 5 GHz into 2.4 GHz band, and that happened in 2003, and that bears the name 802.11g. So 802.11b and g are in 2.4 GHz band. 802.11a is in 5 GHz band. If you look at the 2.4 GHz band and its channels, you'll see that, you remember, we use 22 MHz wide channels. But those channels, as they are numbered in the 2.4 GHz band, are actually 5 MHz apart. And this is the reason why you cannot use channel 1 and channel 2 at the same time in the same location. They're just 5 MHz apart. They're going to overlap. So what you have to do is, when you use that numbering system, is keep in mind that it was not designed for Wi-Fi, and translates that numbering system into something that can be used for Wi-Fi. And that pushes you to use only 3 of those channels, 1, 6, and 11 that you see on blue and purple here. If you use those 3, you are more than 22 MHz apart from each other, and then there is no overlap between channels, which means that one signal is not going to disrupt the other in the same physical area. So when we say we have 11 or 13 channels, actually these are just numbers. But real usable numbers, we have 3, 1, 6, and 11. In the OFDM world, the transmission is not 22 MHz like it is in DSSS, it's only 20 MHz, which means that worst case scenario, you could almost bring those channels a little bit closer and they would overlap a little bit, but it would not be that bad. This is why in some regions where they have 13 channels, instead of using 1, 6, and 11, they use 1, 5, 9, and 13, but only in OFDM mode, so that the transmission is only 20 MHz instead of 22 MHz. And that works okay for data. It doesn't work well for voice because there is still a tiny overlap between the channels, and that's something that you cannot accept for voice. Also, it counteracts the definition of channels by the 802.11 standard. The 802.11 standard decides that channels are channels if they are separated by 25 MHz or more. So you cannot use 20 MHz separation like we do here and think that you're okay. There is an overlap. This definition came because, of course, initially those channels were 22 MHz wide. So this is why the 802.11 decided that 25 MHz separation needed to be there for those channels to be non-overlapping. Here, there is some bit of vocabulary you have to be aware of. When two channels are 20 MHz apart, they are adjacent. That's the name of the 802.11. However, you'll find countless papers in the internet, in the industry, where channel 1 and 2 are said to be adjacent just because they are just next to each other. But understand that this is not true per the 802.11 standard. 1 and 2 are overlapping, and only 1 and 6, and then 6 and 11 are really adjacent. So be careful, because the CCNA wireless uses the 802.11 naming convention, So if you say that 1 and 2 are adjacent, you're wrong. They're overlapping. 1 and 6 would be adjacent. And there is another term that says if channels are 40 megahertz apart, they are alternate adjacent. That's a name that you find less often, but that's also something you find in the 802.11 protocol. And the reason why we talk about 25 and 40 megahertz apart as making sense is because signals are filtered as they are being sent by transmitters and received by receivers. And it looks something like this. This is a DSSS filter, which means that when you design a circuit to send or receive, you'll design a key frequency that is the one that's at the middle with the FC, and you will have what we call a mask. That mask makes that every signal that is at least 11 megahertz away should be at least 30 dB weaker than the main signal. And your circuit is going to have that filter, that is to say a physical display that will absorb any energy on the side that would make you break that rule. Anything that is 22 megahertz away or more from the main frequency has to be 50 dB weaker than what you send at the main frequency. Your filter is going to make sure of that. For OFDM, the mask is slightly different. You see that we are not working exactly with the same numbers, but logic is the same. Every transmitter, every receiver has a filter, and that filter makes sure that the transmission is within what is described by the 802.11 standard and allowed by the protocol. So that even if you send some signal on the main frequency and your circuit sends some signal also aside of that main frequency, the filter is going to make sure that this signal is not going to leave your system. Remember, we said that in 5 GHz, we also have channels, but those were numbered with 802.11 in mind. And that's better because those channels are directly 20 MHz apart. And as you may remember, in 802.11a, 5 GHz, there is no DSSS. There is only OFDM. So there is no 22 MHz wide transmission. There is only 20 MHz transmission. So 20 MHz separation is perfectly fine. Although, again, it's better to always leave one channel if you can between two access points in the same neighborhood so that there is always, a tiny overlap between these channels so that this tiny overlap doesn't disrupt you too much. But even when you do so, you have much more space in the 5 GHz band than you do in the 2.4. Of course, there is still this story about these radar DFS affected channels, but that gives you more space. Still, we need that space, and we use it all. And there are some efforts from the industry to talk to the FCC and other regulatory domains, bodies, to try to free space in the channels that you see in gray here, which are basically between the channels that we have the right to use. We like to extend the spectrum to those channels so that we have a continuous spectrum in the 5 GHz band. By the way, the same effort is ongoing in the upper part of the spectrum beyond channel 165 to try to also get more channels on that side. It's an ongoing effort, and by the time you watch that video, maybe some of these channels will have been adopted. But it's a long effort, it takes years. Unfortunately, because the 2.4 GHz band is ISM, many other devices are transmitting, and we mentioned those. The thing is that for us, what matters is not only that they are using the band, but also that their power is different. Our power is up to 20 dBm, which is 100 milliwatt now, is something you master completely. Some other devices may be sending the same amount of power, that's the case of Zigbee. But some other devices, like Bluetooth, may be sending a lot less, and they will not be disrupting us too much until you have plenty of those. If you have plenty of those, and if they are close range to your access point or your system, then they may be disrupting you. And the thing is, Bluetooth devices, where do you find that? For example, in a Bluetooth headset. And the Bluetooth headset, where do you use that? Well, typically on your phone that has Wi-Fi. So your Bluetooth headset is going to be typically close to the device you use because that's where you use it. You need to be in range of that device to use it. Your Bluetooth mouse also may be very close to your laptop. So it's very common to see some Bluetooth interferences just because Bluetooth is very close, although it's not very powerful. And of course, if you have many Bluetooth devices, it makes things worse. And there are also some other interferers that are using the same frequency band, but they are a lot more powerful than we are. For example, cordless phones. They can go all the way up to 300 milliwatts, where we are limited to 100 milliwatts. So of course, although they don't use the same spectrum as we do, because they use the same band, and because the power is 250 to 300 milliwatts, depending on the country, it's going to be very disruptive to our systems. In the same logic, analog cameras are going to be highly disruptive as well because they have the same type of power, 250 to 300 milliwatts. A good thing is that more and more devices made today that are not Wi-Fi are Wi-Fi friendly. You find a lot of cameras today that are analog, they are ISM, but they understand Wi-Fi and they detect Wi-Fi transmissions and they try to jump away from the frequency used by your access point. So that's very good. Unfortunately, if you have all channels being used by your access points, those devices are still going to disrupt your signals because they have nowhere else to go.